like I said earlier, don't sit down too long for 45 minutes. You know, we need to observe ergonomics. And you're welcome to today's meeting. Sit back, relax, and enjoy the technical lecture. Thank you, and back to you, Engineer. Okay.
Thank you very much, Engineer Chris Egwatu. You can't get it better anywhere else with HSC remarks other than when it's coming from Engineer Chris Egwatu, the one who has been at the helm of affairs of HSC at even the council level for some time now. Thank you very much, sir. We appreciate the safety remarks you've given to us, and I'm very certain that we would abide by them and run with them in the course of this program and even beyond. Yeah, so again, I'd like to apologize that my video is not on. I'm trying to manage my bandwidth. I started observing low reception within the past few days in my locality. So apologies that I'm not able to open my video. So but I'd like to also crave our indulgence. If you can, and if you want to speak, you should open your video so that we can see you and feel you. Thank you very much. So at about this time, let's open the floor for the section chair to give us the opening remarks and steer us into the technical lecture program proper. I'd like to invite Mr. Tami Biambo, the section chairman of the Society of Petroleum Engineers, Warri Nigerian section, to take the podium. You're welcome, sir.
Yeah, thank you. Okay. I'm really delighted to be here because I think this is a very, very technically rich discussion. I mean, this is a a, a kind of lecture that you probably pay some good money to attend in some clients, but courtesy of SP Section 104, we bring in a very seasoned lecturer to present this topic, well controlled in our industry, upstream. The key deliverables, delivering wells, exploration wells, appraisal wells, development wells, injector wells, all sorts of wells, but all of them require to be delivered safely. And one incident on well control can not just impact the reputation or business of a particular company, but even other companies within the industry might be impacted, especially in these are very environmentally sensitive areas. And therefore, whenever you talk about well control, it's something a very topical issue, and attracts a lot of interest. So today we'll be having the opportunity, pleasure of having Tova presenting to us. I just want to ask everyone that are here, industry professionals, young professionals, students. I know in some locations there are a couple of people in a room. Please pay attention to this. Come with a heart open to learning, a learner's mindset, and do ask questions. And you have not just over on the call, I see a lot of industry professionals that can provide and do justice to your questions. So on that note, I hand back to you, my MC. Okay.
Thank you very much for that one. That was very apt and on point. Thank you so much. So if you have not pulled out your writing pad and your pen, I think this is the right time to do so you don't miss out on any part of this program. But before I go into that, I'd like to acknowledge the presence of very important personalities on the call. Everyone is special and welcome, but permit me to recognize the presence of our immediate past chair, person of Dr. Eddie Okon is on call. You just heard from the current section chair, Mr. Tami Biambo, who have the program's chair on call. Like the section chair said, we have a lot of industry professionals who have technical knowledge of the subject matter on call. So you are all welcome, and we are glad to have you. So right about this time, I'd like to invite to the podium the facilitator of the program, is Mr. Olorutoba Ishe. Permit me if I have not pronounced the name correctly, but I know he's the West Learning Advisor and certified trainer with the Share Petroleum Development Company of Nigeria. At this time, without much ado, uh, I would like to invite Mr. Oloritumba Isherua to the podium to take the lecture. Thank you very much, and we are glad to have you here. Welcome, sir.
Okay, thanks a lot, Mr. Okay. I'm going to want to share my screen. So please just let me know when you can see my slides as well. Just let me know when you can see my slides in slide mode.
Yes, I can see it. I believe others can see it.
Okay, great. And my audio is good as well.
Yes, it is
sharp. Okay, thank you. Okay, so let me start by saying a big thank you to the board of the Section 104. It's a privilege to have this opportunity to share some knowledge about well control generally. So I'm really grateful to Sakami and the board, and thank you for this opportunity. So by way of introduction, my name is Olautraba Ishewa. As Mr. Oke said, I'm the learning advisor for wells in SPDC. Also teach a couple of courses from well control to stop pipe and different courses at our training center. So this evening, I'm going to take us through what I've titled Preventing Well Control Incidents. And by way of agenda, I'm going to discuss very briefly why preventing well control incidents is important. We would look at some impact of well control incidents. Then what I would then do is to do a deep dive, just focusing on about 4 key areas. So people, principles, procedure, equipment, and then we will definitely have time for question and answers. Of course, typically such a very critical topic like this, would be spent. You would normally use hours in the classroom teaching all of this, but what I would try to do is just to bring out relevant points for our knowledge, and then we can also learn from one another. So why is well control important? Let me start by saying that, of course, there's a difference between a kick and a blowout. And a kick can be defined as when you initially have an inflow of reservoir fluids into the wellbore. And that basically is just a kick. So for some reason, you've lost what we call primary well control. You have a kick, inflow or influx of reservoir fluids into the wellbore. And if that flow is not controlled, then it escalates to what we would typically call a blowout. And if you look at the potential consequences of a blowout, it's usually huge. The consequences of a blowout would typically result in fatalities, loss of lives, damage to equipment, damage to reputation, significant impact on the environment. This slide just speaks to a couple of pictures of some of the incidents that have happened in the last couple of years and going down some time back. I'm sure many of us will remember the Macondo incident in 2010, where about 11 people lost their lives. And in terms of cost and reputation, there was significant damage, right? Recently, this year, actually, March, somewhere in Central Africa, Gabon, about 6 people lost their lives due to well control incident. About 6 years ago, I think 2018 in Oklahoma, the US, Prior Trust, we had about 5 people losing their lives as well. And that's just in terms of lives. There's also significant impact, with regards to assets, environment, and so many other things, right? And that's why we have this session, right? So it's important that we understand how do we prevent well-controlled incidents from happening, and even when they do happen, how do we manage it? How do we enter what we call the recovery mode to prevent it from escalating. In 2021, IOGP, the International Association of Oil and Gas Producers, released a report that showed that of a couple of incidents that were reviewed, majority of those in terms of the causal factors was due to human factors, human behavior. Some other aspect had to do with barrier failures and then improper assessment of risk or not properly appreciating the risk involved. And then some other bit had to do with not just following the procedure as required. And that's why this session, what I'm going to do, my presentation is going to be covering some of these things because I think it's quite critical. One of the things I'm going to show you in a couple of slides to come is that even if your equipment are fit for purpose and functional and spot on, even if you have the best procedures and programs in place, you also need to be considerate, or you need to consider the human behavioral aspect. This is an aspect that's really not been in the industry for so long. Post Macondo, it's come up, and IWCF and other well-controlled regulatory bodies have tried to embed this even in terms of training and competence. Okay, so impact of well-controlled incidents. I showed you a couple of pictures, right? Apart from downtime, non-productive time, there's significant impact in terms of cost, significant impact in terms of equipment damage, and exposure to hazards. Remember, of course, you are in the oil and gas environment, and all these things are flammable, right? So HSE impact, deaths or injury. I reeled out a couple of numbers, which is quite sad. Of course, you also have in terms of pollution, whether it is air, land, or water. The remedial costs post Macondo incident cost billions of dollars just because of the impact on the marine and the water body, right? Same with land and even the air as well. Of course, you put in the risk, you put in population close to that place, especially land locations at risk and all of that. You would have to defer production, everything shuts down, and then of course, damage to equipment. Significantly as well, your company image, or what we call reputation, right? There will be a lot of questions asked about your ability, your capability to deliver going forward. And then of course, you could have a couple of effects in terms of the reservoir, right? So, and that's why it's important knowing that, when well-controlled incidents do happen and they escalate, people can die, equipment can be damaged, the environment can be affected, assets can be significantly impacted, and that's why it's important we know, and we would look at it in these four broad areas. So for people, I'm going to be discussing a couple of things around people, around the principles. Like I said, because of time, I'm just going to touch a couple of principles. There's so many principles governing well control, but we'll just touch a couple of them, and then we'll look at procedures. If your well control incidents have happened, what then do you do? How do you recover? And what are some of those equipment that help you manage or mitigate against such events like this? Yeah, so I'm going to continue with people. So let's look at people. Like I said before, research has shown that many incidents are due to human errors. In fact, I mentioned more than 70% of that is due to human factor. We're talking about behaviors, right? So you can have your equipment perfect, you can have the best programs, but then, what about the people bit? And one of the things the IUGP did was they looked at the aviation industry. Yes, if you look at the number of wells we are drilling or working over activities in a year, it is not anywhere compared to the number of planes or aircraft that fly every day. And yet we hear very few plane crashes happening. Yes, they do happen, but they are very few, right? Compared to the number of planes flying, every single hour all over the world. And one of the things that, the research showed and the oil and gas industry decided to adopt was that pilots typically go through some sort of training, not just technical training, but some training that has to impact on their, or that has good impact on their human behavior. So we're talking about things around decision making. We're talking about things around situational awareness. We're talking about things around communication, teamwork, and leadership. And it's been shown very extensively that these five elements, major elements of human factors, are critical if you want to prevent well-controlled incidents from happening. What would make the driller, for example, if he sees an alarm that the kick is about to happen, decide to just pick up his phone, and instead of shutting in the well, he decides to first call the company man, and he's struggling to call the company man. The company man is probably in the rig canteen eating food, you know, and he didn't shut in the well on time. And then of course you have significant volumes coming in, and before you know it, it escalates beyond control. Why couldn't he exhibit that necessary leadership or decision-making skill to shorten the world on time? Why can't people working together on the rig work properly to say, okay, these are my well-controlled equipment, this is what I should do, this is doing it at the right time. So these five elements of human factors are important. Situational awareness, things change. One of the things that has been shown, from a review of well-controlled incidents is when you have shifts, when you have new, like a tall shift, people come in, maybe it's a 12-hour shift, people get, you know, take a little bit of time to warm up and all of that. Sometimes some couple of errors usually happen that period. What about handover, right? I'm leaving as the supervisor on my tour sheet. How well do I capture exactly what happened, right? Communication. What about situational awareness? Things have changed. You did a test of your equipment, for example, of your BOP equipment, and it didn't pass. And you chose to ignore it, forgetting that when an incident actually happens, that's one of your barriers. And that barrier already is not fit for purpose, right? So these five elements are actually important. And one of the things that based on recommendations, even globally and even for us locally, one of the things we try to embed is this what we call this human performance principles, right? So now we're not just focusing on technical training. We are using, if you look at the picture showing here, this is a simulator room that we have at the SPDC training school, where what we do in there is not just teaching the theory, we test their response, right? So they are drilling a well, there's the alarms and all of that, and we see how well do they respond, their decision making, their communication, they are working together as a
Yeah,
team. So a couple of simulator trainings I've done, well controlled. What I would do is I would typically take a rig crew. I will bring in a driller, I'll bring in an AD, I'll bring in a DSV, about five of them, and put them in there and simulate a well controlled incident. And then I watch and observe how they respond, how they work together as a team. And initially, you would see, oh, there's a little bit of, of instability or shakiness. And but over time, their response becomes better. And that's why, again, that's what the aviation industry has done over the years that has given them very good outcomes. And that's the shift now, that it's not just about the equipment, it's not just about the procedures, but the human factors. And simulation-based learning is a very good thing. A couple of 2 months ago, I facilitated training for about 40 rig crew people, and it was quite interesting watching their interactions and getting them to understand better. The other aspect, apart from trainings and certifications, is the aspect of drills, right? So drills test your response. Oh, there's a drill, we're giving the safety briefing, and they said, oh, if there's a drill, do people respond? So I simulate well control, issues, and I check their response time, and I know that okay, these guys need to sit up, or they need to be more, or they need to be ready, or they need to be prepared. So your drills do not just only test the state of the equipment, not just test the state of the procedures, but they also test the readiness, and the competence of the crew. And the whole idea is to do this as frequently as possible, especially when you consider the competence of your crew. So if you have a lot of new hands, then you might need to bring them on board quickly and do more drills and get them ready, right? Okay. So we look at principles. We've discussed people, human factors, principles, the 5 elements: leadership, situational awareness, decision making, communication, and teamwork. And now we look at principles. I'm just going to touch, especially because of some of the students in this call, a couple of the very important principles in well control. One key important principle is hydrostatic pressure. Is that term we call hydrostatic pressure. And basically, hydrostatic pressure is just a function of what we call the density of the fluid or the liquid, and the height, right? And it's important, when it comes to primary well control, that hydrostatic pressure principle, as simple as it sounds, is probably the basic foundation, is a key component. And what that means is that if I get, for whatever is my fluid barrier, if I get the density right, if I get the the height right, or the fluid level height right, then I will be able to maintain what we call, for drilling, primary well control. So your hydrostatic pressure equation basically speaks to density, and to height. So even if you have the same density of fluid as this example we showed, where your density is about 0.585 feet, what this tells you that at different depths, right, it exerts different pressures, right? So even if my well, I'm using a mode of 0.585 psi per foot to drill a well, if I do not keep that well full to the appropriate height, then the hydrostatic pressure is not the same. So hydrostatic pressure is a function of the density of the fluid and the height. Again, density. So if I'm supposed to use 0.585 psi per foot mode, and the density drops, maybe for example, your drilling fluid is in a tank, and that tank is exposed to rain, and rain is falling, and water dilutes it, you know, that density is no more 0.585. It's dropped to 0.57. So the hydrostatic pressure has changed, and that key element of maintaining primary well control, has changed as well. The second principle is the principle of barriers. Your barriers can either be mechanical or fluid. When you are drilling, your primary barrier is your mud, your drilling fluid. And that barrier is driven, again, like I said before, by the density of that fluid and the height of that fluid. So I need to keep my mud density as per plan. I need to keep the height of the mud in my well as per plan. Right. And if that barrier fails, you also have secondary barriers, which is your blowout preventer. And we'll discuss that very quickly. Right. So you have mechanical barriers, you have fluid barriers. So if my fluid is going to be a barrier, then I must ensure that the hydrostatic pressure, density times height, of that fluid is greater than the formation pressure, basically, right? And you must be able to circulate and basically maintain that density again, because we talked about density. You also must be able to monitor for height, because remember the function of height, right? So all of your barriers, whether it is mechanical barriers, your fluid barriers, what we typically would do is to test them, and not just test them. You would typically need to document them as well. So you have different barriers for different operations, whether you are drilling, whether you're in the workover phase, or whether you're in production. You have both fluid barriers and you have mechanical barriers. Your wellhead is a barrier, your BOPs are barriers, your cemented casings are barriers, you know, depending on the phase of operation you are, your Christmas tree, your tubing hangers, all of that can be barriers depending on the particular operation that you are going through. The third principle is the principle of risk management. Going back to barriers, when I teach rig people, I always like to emphasize the principle of barrier. And I tell people that the fluid is an important barrier. So sometimes when I'm working as a supervisor on the rig, and I'm telling them, make sure your mud tanks are properly covered, let water not dilute the fluid and all of that. And people are wondering, why am I making so much hassles, right? It's because, like I said before, if that density is reduced, then I already have issues with my barrier. So I always teach that barrier principle to tell people that you have barriers, primary, secondary barriers, and it's important that your barriers are fit for purpose. The next principle is risk management, right? So there are certain things that can release. Basically, you have hydrocarbons down there under significant pressures, under huge temperatures, and those things are hazard. Anything that has the potential to cause harm is an hazard. And there are things that can release that hazard, what would typically cause threat, right? So you want your hydrocarbons to be contained in a safe manner. When you are drilling, like I said, your mud is that primary barrier. And then if your primary barrier fails, your secondary barrier blowout prevent that to prevent blowout. But there are certain things that act as threats, that can release these hydrocarbons to surface. And I'll give an example. I'll go back to mud, for example. I've said hydrostatic pressure, key component of primary well control is density times I. How do I check my density of my mud? I use a mud balance on site at the rig site. If I do not have a mud balance that is calibrated, I'm going to be reading values of density that are not very correct, right? So that is already a threat. If you have a mud man who is reading that mud density and is not competent, he doesn't have the necessary certificate, he's not skilled, he reads the wrong value, then you are also in trouble. So there are certain threats, and whether it is human factor or equipment that can release, those hazards. And when they happen, when those hazards are released, you go into a control recovery measure before you prevent it from escalating, basically. Remember, I said the consequences of well controlled incidents, when they do happen and they are not controlled, can be quite devastating, especially for blowout, right? So you want to prevent a release of that hazard from causing further damage, right? And you can imagine on a rig floor, if you have hydrocarbons, very flammable, coming to the rig floor, you have generators working up and down. You have a welder who is working there. You have some grinding machines and all of that. You basically have an ignition ready. And with that flammable hydrocarbon coming up, is a recipe for fire, right? So you want to be able to understand this principle of managing risk. If your situation changes or the operations change, you must be able to understand the new risk that are associated. So we always want to manage our risk, right? Your program is a preventive barrier. Having a very good procedure, having your mud checks from time to time, every 30 minutes, for example, is a good procedure. Having a calibrated equipment, calibrated mud balance, is a very good preventive barrier, right? Once those incidents happen and you enter recovery or escalation mode, you're basically entering emergency response plan. You can imagine the Macono incident that happened. You have the source of hydrocarbons feeding the fire. The only way you can stop that fire from burning is if you do something to that source. And so what do I need to do? You need to maybe drill what we call a relief well, some location or some distance away to intersect that source and quench it. And you can imagine how long that would take you. Get a different rig, get a new location. If it's land, do location preparations, get new casings, get new drilling equipment and all of that. When blowouts happen, the recovery usually will take a very long time. You don't want that to happen. Drilling window. So drilling window is defined by, remember I said primary barrier is your mud. That mud weight is usually between two factors. The lower limit is your pore pressure, your formation pore pressure. So what that means is that I want my mud weight, the hydrostatic pressure, density times height of my mud, to be greater than the formation pore pressure. But I do not want it to be so great that it is greater than what you would call the formation strength, what we call fractures. So you can imagine if I have a bottle of water that is full and I have holes at the bottom, what will happen is I will start having the fluid leaking down. And once I have fluid leaking down, what happens to the level of water in the bottle? That level of water drops, height drops. Hydrostatic pressure is density times height. Your height has dropped, your hydrostatic pressure has dropped. So your barrier is already failing, right? So you want your a drilling window to be, between the lower limit of your pore pressures and bore stability or collapse rate, and the upper limit is the fracture strength. And typically, we want to always operate within that window, and that's why your mud weight is usually designed to be within that window. Yes, there are some regions where you might have what you call a narrow margin. That window might be very small, but you have systems in place, what we call managed pressure drilling, to address such issues. So basically, if your mod hydrostatic pressure is greater than the formation pore pressures, then you are fine. Once you lose that overbalance, then your formation fluids will begin to enter as a kick. And if you do not control that, it escalates to a blowout. So what are the three levels of well control? I've talked a lot about primary control, and I said, remember, hydrostatic pressure is a function of your mode, weight, or density, and keeping your hole full in terms of height. And then the secondary method, which is now your control and recovery, is what you call your blowout preventer. And then the final one, if that fails, like in the Makono incident, you are basically at the tertiary control measure. What you basically have to call in specialists, maybe the boots and boots of this world to do that. And you really don't want that to happen already because you are significantly out of control. Okay, so we always strive for primary control, especially in drilling and and then walkover operations. When do we lose primary well control? We lose primary well control when the bottom of pressure or the hydrostatic pressure density times height is no longer greater than that formation pressure, right? So the way I always explain it is there's an equation. My mod hydrostatic pressure density times height must always be greater than my formation pressure on the right hand side. That formation pressures for some reasons can be greater than what you expect. Usually that will happen in exploration wells, where at best you predict that pore pressure. So you were predicting that my formation pressure will be 0.52, and you designed your mode hydrostatic pressure to be 0.54. But when you drilled, the actual formation pressure became maybe 0.56, and then you go under balance. So you call that a drilling kick, right? That is usually expected in exploration wells. With development wells, you have data over time. You have very good knowledge of pressures, right? The second bit is, so that's the right hand side of the equation. The left hand side of the equation is your hydrostatic pressure, the more density times height. So anything that affects the density causes it to drop, you will lose your hydrostatic pressure and your BHP. Anything that causes the height to drop, you lose that. So if your fluid level falls or you swab and that affects the fluid level as well, you are going to lose primary well control. Swabbing very quickly is just, there are two levels, you hear about swabbing and all of that. Basically, when you are pulling your pipe out of hole, what you are basically doing is to fill back the volume displaced. So you want to fill your hole back as you're pulling out the pipe and use your chip tank to do that. So you want your mud level to always be full. If you pull too fast, you're pulling faster than the way you are filling back, your level will drop significantly. If your mud is too viscous or too thick, it's not flowing as quickly as possible to fill back your hole as well, you can have what you call low volume swabbing, right? And this is quite very serious. The incident that happened this year, I think in Gabon, was, or one of those incidents that happened recently was due to swabbing. So swabbing can be very dangerous as well. So if I'm pulling too fast for high volume swabbing, basically what that means is you might have your bits balled up or you have significant pack up. So the fluid level in your annulus is not dropping. This is the annulus, it's not dropping to fill that place. So you are creating a vacuum down there. And because of that, the fluid level in the drill pipe will drop to fill that vacuum. And once that fluid level drops, right, you are going to have significant bottom hole pressure dropping as well. That can be very dangerous in, what you call very large holes, like top holes, where your hole size is big. So basically, you are filling a very big hole size from a small volume of pipe. So the fluid level in the pipe will drop significantly because it's going down to fill a very, very large vacuum. And that can be very dangerous as well. Yeah. So I've made a couple of definitions. I said kick is inflow, and if it's not managed well, it would lead to a blowout. And I said, remember, if you are drilling exploration wells, your formation pressure is significantly greater than your mud hydrostatic pressure, you would have what you call a drilling kick. Whereas the other bit is usually swap kick. And research has shown that most of the well control incidents when drilling is actually due to tripping errors, right? Not keeping your oil full, not monitoring your mud density properly, and a couple of things as well, right? So when you have a kick, whether it is drill kick or a swag kick, you will typically have warning signs. If it's going to rain, typically you will see the signs. The cloud will change. You might get some thunders and all of that. It's the same thing. We have what you call warning signs. Warning signs that, oh, there's trouble boom coming, right? So you have kick warning signs. Then you have kick indicators. Your kick indicator is a strong signal that your kick has happened. But with kick warning signs, does not necessarily mean that the kick has happened. It's a sign that something is about to happen. So kick warning signs, you have what you call, drilling break, change in your rate of penetration. you know, you would have your mud chloride content changing, increasing. Your formation has its fluid has its own chloride content. When the chloride content from the formation fluid is mixing with the chloride content of the mud, you will see an increase in the overall chloride content you are measuring, right? You will see significant gas readings. All of a sudden, that formation pressure that was put under control is beginning to overpower your mud hydrostatic pressure. So you see gas readings coming up, and significant change in mud properties, changes in cutting size, what you call splintered, cuttings, cavings as well will come out. Those are key warning signs, and you need to quickly readjust. Either you're doing a flow check, circulating, just make sure you are ready to deal with that. But in terms of kick indicators, sure signs that the kick has happened, you basically have, you know, three basic ways to know. First one is to know is an increase in return flow rate when you are drilling. You know, you would see all of that happen. So you will see what you will call your pit volumes increase as well, and your flow should increase as well. So in the return line, all your fluid comes out through the annulus, through the return line. You have in that return line, you have what you call a sensor. You see this paddle, fluid will be eating this paddle in and out. This measures the rate of return of the flow of fluid. If there is a sudden increase in that rate of return of this fluid, that means more fluid is eating that paddle. Where is that extra fluid coming from? It means you might have a kick down there. If the rate of return of fluid drops significantly, what has made it drop? It means you might be losing what you call losses. You might be losing your fluid level might be dropping as well, and that can be dangerous as well. And then, of course, you have your pit volume basically captures the total volume. So it's a closed loop system. I expect to see maybe 100 barrels. Why am I seeing 105 barrels? Where is that 5 barrels extra coming from? It's a sign that something has come in from your formation, to mix with that 100 barrels. That is, that means you have a kick and you need to shut in the well, right? The third method is when you are tripping, right? Because you want to keep your oil full at the last every single point. The way you're tripping means you are running in and pulling out of pipe of the well. So we have a method of managing that tripping, and we use what we call a trip tank. So a trip tank is a very small volume of tank that can record significant changes in the height, in the level of fluid. Basically, what that means is that if I'm pulling out of hole, yeah, I'm pulling my pipe out of hole. When I'm pulling my pipe out of hole, I'm going to want to fill back that volume of steel that I've removed with fluid from your trip tank. So if I pull out pipe equivalent to volume equivalent to 3 barrels, my trip tank will feed back 3 barrels. If my trip tank only feeds back 2 barrels and my hole is full, why is it two instead of three? Where is that one coming from? That one is coming from somewhere below the ground. Like you have a kick. This for me is one significant reason why we have so many incidents, while drilling. Many rig people do not know how to measure, use their trip sheets to record these volumes, right? So if your primary well control has failed in drilling, which is your mud, then you move to the secondary well control. And that mode you are in, recovery mode. So you need to shorten the well, right? So you have two methods of shortening the well. You have what you call your soft shortening or your hard shortening. Basically, many operators prefer the hard shortening the well. So what that means is my mod hydrostatic pressure has failed. So what I need to do is to short what you call your blowout preventer. So you shorten the annulus. So you do what you will call your space out, and then you shorten the well. The difference between hard shortening and soft shortening is usually in terms of the choke, lineup, right? So if you're drilling with 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 hard shortening, this your choke is usually um, closed, is fully closed, and this valve, what you call an HCl valve, is usually closed. So I'll space out and close my BOP stack somewhere here, and then I can come and open this valve and read the pressures. But in soft shorting, this choke is usually open, and instead of closing the BOP stack first, you first, open this HCl valve, and then you close your BOP stack, then you come and close your choke. School of thought about the different methods, but for many operators, we prefer to close in. The less volume of influx you take in, the less pressures you would eventually see. And now when you're shorting the well, you're in recovery mode, you now need to be able to recover. So recover is that kick, that influx, that stranger. I want to take it out in a controlled manner. When I teach, I always tell people that, the way I would chase a visitor from my house, is different from the way I would, in quote, chase, let me say, a family member. If I want a family member to leave, I need to be able to do it in a very controlled manner. Same thing if you have a gas influx or you have an influx or peak in the well, you need to take out that influx in a stable, controlled manner. If not, if you just drive it out, it will cause serious damage for you when it is leaving your well. So there are different methods depending on the scenario. If you have strings and you can circulate, you have a string in hole and you can circulate, you typically want to use driller's method. Each of them have their pros and cons, but driller's method while drilling is usually the preferred method. If you are doing walkover wells, you might want to do reverse circulations, which is pumping into the annulus, and taking returns. It's reverse, taking returns to your string through a communication path. Right. So there are different methods, wait and wait. Wait and wait, you are waiting while you are preparing a mod now with enough pressures to overcome, take back control, basically. But for driller's method, what you are doing basically is two circulations. Drive out the stranger first, then you can, while you are preparing the greater mod weight, and then when you have driven out the stranger, you can come and pump in the greater weight. But for wait and wait method, you will wait, right? And then once you have your greater mod weight before you pump it will, yeah. Bulleting, you might want to do that if you don't want your peak to get to surface. If you are drilling in regions, for example, where you have H2S that is quite dangerous at surface and at risk to people, you want to bullet that H2S back into the formation. Yeah. Subsurface people and ourselves will typically not like bulleting because of the potential damage to the formation. Now I'm going to just wrap up very quickly because of time, right? So the last bit is the well control equipment, and there are different things, different um, aspects in your well control equipment. So you have what you would call the blowout preventer. Your blowout preventer is just a collection of different devices or valves or tools that helps you now in the secondary recovery mode. So you have what you call in a spherical mode this annular preventer that can close around any size of pipe. Even if you have a pipe in hole, you can close in using your annular. It has some annular elements that can close in on the well. You have your blind shear ram. This is usually your last resort. It will cut off, right? It will cut off and seal the hole. And because it's cutting off the pipe, that pipe will drop down to bottom. So it's your last resort. You have your pipe rams. Your pipe rams close around a specific size of pipe, right? So basically, your pipe rams close around a specific size of pipe. So if you have a pipe, a 5-inch pipe ram, your 5-inch pipe ram will only close around, a pipe that is 5 inch in terms of OD. You have some other rams, what you call your variable bore rams. Those will close around a range of size of pipes. So whether it is from maybe 4 inch to 7 inch, as the case may be, it will close around that range. So you can have different configurations for your blowout preventer. This is your secondary recovery method. How do these things close? They basically use hydraulic fluid to move some pistons to close and seal around this pipe. So they are going to close and seal around this pipe. That hydraulic fluid comes from what we call the Kumi unit, where that energy is stored. And when you activate and push your your BOP control panel, sends some signal and pushes those fluids to close these preventers. You must test this equipment. What you do function test, you must pressure test as well the connections, just to make sure that everything is fit for purpose. When I want to bring out the stranger or the gas out of well, because I want to bring it out in a controlled manner, I'm going to direct the flow through what we call a choke manifold. The choke manifold is basically a collection of valves that allows you put some back pressure. So it's basically you have an orifice. If your bottom pressure is increasing, you can close that orifice. That puts some additional back pressure for you. If your bottom pressure is increasing too much, you can open it up. So that's why you bring it out through a choke manifold. And if it is gas and mud coming out, it goes to what you call a mud gas separator, where the gas is vented, through vent lines and maybe overboard, and then you have your mud going back to the mud pits. How do I control this choke manifold? I use what we call a choke panel, a remote choke panel to control these valves and secure my well. So you have different blowout preventer equipment, whether it's the annular and the ram type, whether it's the 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 share rams, and all of that. One last bit I would like to say is that your preventers, your BOPs, they seal off the annulus. So if I have hydrocarbon coming, I have sealed off the annulus. But this hydrocarbon can still come in through your string. And so typically what we'll do is to install what we call a full open safety valve on top of the string, if you are tripping in the well, and isolate this string. If your pipe is connected to TDS, then of course it has those measures. But if you are tripping out, you install this valve. So this isolates in, so the hydrocarbon cannot come in through the annulus, or inside through the string. There are barriers preventing that from flowing and coming up to the environment. Because of time, I try to rush a bit, but that's where I would pause for now and take some questions as well. Thank you so much for this opportunity.
Yeah, thank you very much. Thank you so much, our facilitator, for today, for this wonderful session. Like the section chair rightly mentioned earlier, this is something you would pay a huge amount of dollars for, because you can't easily come by this. Thank you very much for this lecture. And for me, I see that it makes a lot of sense, a lot of learnings and insight from it. Actually, it talks about a lot on the volta operationalization, trying to keep your hazard on the left-hand side to our lap level so that the top event does not happen. And even if you now begin to see signs of top events happening, trying to put systems and controls in place so that it doesn't lead to the consequence. Thank you very much, sir, for this one. I would leave the floor open for questions. I can already see comments in the chat box. But before that, also permits me to acknowledge the presence of other dignitaries that stepped in while the lecture was ongoing. We have our one-time section chair and section director on call, Madam Magdalene Moore. Thank you, Ma, for joining us. We also have other dignitaries. We have Dr. Sarah Willie on call. Thank you very much, Ma, for joining us. I already introduced the section, past section chair. We have a lot of section board members on call too. Engineer Christopher Egwatu, we heard from him earlier. Dr. Adetona is on call. We have Mr. Christian Engineer Christian Ng. We have other dignitaries on call. So thank you very much for joining us, everybody. You're welcome once more. We are waiting for our questions in the chat box, and also if you want to speak, you can signify by raising up your hands. Then we'll call on you to speak. So we'll just give it a few minutes for questions. However, already we have some beautiful comments in chat box. Yeah, we have Justice Vidigon called to the immediate pass YP chair Port Harcourt section. Thank you very much for joining us. And he says, thanks for a very insightful section. Thanks, Engineer Toba. We have Andrew Abadu say, also a board member, say, thank you so much. Bobomi Bimo Bere, thank you, sir, for that session. Excellent delivery from Paul Alabi. Gloria says, thank you so much. So we have a question here. Second chair is also adding his voice to thank Engineer Toba for the interesting lecture. So we have a question from Ebimo Bere Bobomi, and it says, I just want to know if the BOP preventers are calibrated this time. Engineer Toba, you might want to respond to that.
Yeah, so your BOPs all have a rated working pressure, right? So basically, that is in many ways driven by the maximum pressures you expect to see on top. If I'm drilling high pressure, high temperature, wells, for example, then you want a BOP that has a rated working pressures that is probably up to 15,000 psi. So it can handle anything 15,000 psi on top. Usually the rams, the annular usually will be slightly rated, might be 10K. That's allowed. So if your pressures also are not that high, you can have 3K, 5K, 5,000, 3,000 psi. BOPs are rated to that. But what you also want to do, like I said, is to test. So function test. You are function testing the controls. So when I go to my control panel, those signals that would send hydraulic fluid, that will activate some mechanism to send hydraulic fluid to push the pistons, and close the shutting the well, right? You want to function test that everything is working well. You want to also pressure test the connections. Everything is about containment, right? So if the BOPs are working well and you're in secondary recovery mode, the hydrocarbons will definitely be contained. So you do that function test every week, and typically we do that pressure test every 3 weeks. But what is important as well is that the rated working pressure for the BOPs are appropriate for the specific kind of wells that you are drilling.
Okay,
And we
thank
have
you very much.
certificates as well. So you would also validate or check and confirm those certificates. Yeah.
Thank you very much, Engineer Toba. And I see the person who asked the question already responded. So I believe the answer is clear. The systems are pressure rated, but we have functionality tests to confirm how they would respond when we need them. And they are done occasionally. Thank you very much for that. I'll just check chat box if we have further questions. Okay, Echo Miops are still pouring in the chat box. Very insightful session, very interesting session this year. I would like to ask if you would leave this slide with us. I believe a lot of us would like to have it and peruse it at our convenient time.
Okay, that's fine. Yeah.
All right, thank you. So another question just popped in. How much time is required to close the BOP in case of well control? That's coming from Mark.
So you have standard times for the different elements. So whether it is surface or subsea, basically there are minimum standard times. So you expect your annular to close within a specific time. You also expect the rams to close within a specific time. So your rams doing for surface, for example, should close within 30 seconds, right? And the annular can take up to 45 or 60, depending on the size of the annular, if it's rated for 18 quarter. If it's subsea as well, they all also have their closing times. Rams might be expected to close within 45 seconds. One key thing to note, especially for surface locations, is that remember I said that your is hydraulic fluid coming down from the Kumi bottles going to push those pistons, right? You can imagine if the distance is very far. So it's going to take a long time for the fluid to hit those pistons and move. And that's why even up to spacing of properly placing your booming units, as well. It's important that they are not too far because that will affect the closing times as well. And that's also another reason why in subsea wells as well, because you are drilling deep water, they have an indirect hydraulic system of closing the BOP to minimize that closing time because of the distance, you are going down deep, beneath water as well. You might have what you call subsea BOPs even down there on the seabed as backup as well. So yeah.
Thank you very much. Thanks so much for that elaborate answer. So I can no longer see questions in chat box and no raise of hands. So I think it is quite clear. And thank you very much for making it very short and rich. It's very rich, yet came in a very good time. So, but yet again, there's another question that says, under what condition is underbalanced drilling recommended? Underbalanced drilling. So you may want to also just state what underbalanced drilling means and then give us response on what condition that we recommend underbalanced drilling.
Well, fortunately for us in Nigeria, our reservoirs are, in terms of permeability and the ability to flow the fluid, they do quite well, right? But you have some regions, especially, in North America, where it's difficult in terms of what you call tight formations, where the permeability is not very good. So fluid is struggling to flow. So you are not going to now bring something of great force to just overpower it. Basically, nothing is even going to flow really. So what you usually would do in those conditions is to use maybe some managed pressure drilling mechanism, just managing. So you have some places where you even need to frack before you can squeeze out some of those hydrocarbons in there. So for the balanced drilling, typically you can use the managed pressure drilling, which is a way of just managing the pressures in the wellbore while you're drilling in under balance. So you can go below, that, like I said, that formation pressures, because fluid flow is not as good as it is. So you have very minimal risk. So all of that has to do with risk assessment based on the different formations. And like I said, you have the NPD system that can help you drill as well.
Thank you very much, Engineer Toba. Thanks a lot for the response to that question. I believe we have answered all the questions, and we can go ahead to the next item on the agenda, and that would be the closing remarks by the program chair, SP Warri section, and then we would be inviting Dr. Adetuna to take the closing remarks. Dr. Adetuna, please.
Hello, good evening, everybody.
Yeah. Good evening, sir.
Good evening, sir.
Engineer, okay, can you hear me? All right. Engineer Toba Ishawa, thank you today. Thank you so much for your wonderful world-class presentation. It's so amazing that Warri is always a pace setter. Because we are still going to engage packages in drilling and well completion. Thank you so much for your time today. And at this point in time, I would like to call on Engineer Dr. Eddie Immediate Pass, Section Chair, if he has any comment to make on the presentation we just heard. Dr. Eddie, I don't know if you're on the call. Hello, Dr. Eddie. Okay. We still have another important person. That is I Square PC. That's our immediate chair, and the person of Engineer Magdalene Umar. I'm sure she's always with us for everything we do in this session, even when she even makes effort to come over to the Warri for any activities that is ongoing. So at this point, if she's still on the call. Hello, madam. Please, are you on the call, ma? Okay, can you still hear me?
Yes, I can
Hello,
hear.
okay, can
Hear
you hear?
Yes.
you. I can hear you.
You
Though
have
I
the floor,
didn't
ma.
get the thing you said.
Okay, we just
Okay.
want you to
Oh,
give a little pep talk on this. Thank you, madam.
wow. Okay. Good evening, everyone. It's really nice connecting with the section on a technical meeting. I'm really, really excited. When I saw the banner for this, I knew that we were in for a very good quality conversation this evening. So I really want to say thank you to Toba for creating time to put together this excellent presentation that has increased our knowledge base, on well control. Thank you so much for it. And I also want to thank the committee that put together this alongside the section chair. Thanks. Apologies, I'm actually juggling between two things, attending this technical meeting and also attending a training at my place of work. So I may not have gotten all the details, but when I looked and I realized that it was the streaming live, I said, okay, I will always do a catch up afterwards. But thank you so much. And I really appreciate your time. Well done to the.
Thank you, ma, for
Okay,
that
I thought
brief.
I was heard. Okay.
Okay, I don't know if we still have Dr. Eddie on the call. Yeah, I saw him earlier. He was on the call. Is he still on the call? Dr. Eddie?
No, Dr. Eddie is
Yeah, good
still
evening.
on the call.
What did
Yeah.
I do again now?
This is Dr. Eddie. We would like you to give a brief pep talk on what we just had today. Thank you, sir.
Okay, well, good evening all. This area is actually my area. So I was just, picking up lessons and taking notes. Beautiful lecture, well delivered. A whole lot of things can actually go on when you are having a well intervention activity. And we cannot really say enough of it. Our guest lecturer today have done a whole lot of justice to it. The key thing about well intervention is that for you to prevent any kind of accident or incident or loss of containment, is just following protocols and following laid down rules are very, very key. They are very, very important. And again, your equipment, safety critical equipment are always key for you to make sure that they are working as at when it's time to do their checks, do their checks. So like I said before, I think he has said everything. He has said it all. And beautiful lecture. I really do hope that we'll be having more of this. As I even speak to you, we're having interventions right now. And this is a quality intervention. And we have BOPs. We have lots of valve, lots of machines here. And so it's just like a reawakening of what we're actually going through at the moment. So I just hope some of us, especially the students among us and young professionals, that they actually took notes, because I took notes. I don't know about them. So thank you very much. And we hope that when next we call you again, you will oblige us your time and your professional knowledge in well intervention, accident prevention, and other things, because I believe that you are made up of a whole lot of things than what we have just seen. This is just a tip of the iceberg. So thank you.
All right. IPC, thank you so much for that. At this point in time, I want to call on the section chair to close out the meeting finally. Engineer Tammy, please, you have the floor to close us out for this meeting. I'm sure our students are proud. We had a large number turnout for this event. Thank you, sir. Engineer Tammy.
Yeah, Dr. Adetona, thanks so much. I thought you had already closed the meeting, but I'm very excited. You all have heard, um, especially after we had a great lecture, the questions that are coming, and I just want to urge the students and young professionals online and those professionals that still need to ask some questions, please, you can send it to any one of us. Yeah, we'll pass it through Toba. And if he gives us the answers, we'll give them. And Toba also, if you give permission for us to share your slides, we can share it to those participants as well. So on that note, I just want to say big thanks to everyone for your time. Great section. Back to you. Okay.
Thank you very much, Section Chair, and everyone who has spoken. So we heard it loud and clear. If you have questions, you can pass across, and ways will be found to get the questions across to the facilitator for us to get responses to them. So we are done with today's session. Wonderful session. And I like to give our indulgence. Let's look out for our flyers and programs whenever we have them. They are always very important opportunities to network, to bond, and to learn new things, to gain new insights into new things that we don't know, and even those that we know, and we need to develop from them. So right about this time, I'd like us to open our videos so that we can take the photograph section. Paul Alabi, Madam Tessie, I guess you guys would help us to take the photograph. So please, let's open our videos to do this, please. Thank you.
All right, please let's turn on our videos and take a picture before we close out for today. It's been a wonderful time together. So, all right. We need more persons to turn on their cameras. Right. Engineer, okay, I see you. Mr. Oluntoba, I see you. Dr. Luashin, I see you. Mr. Tama, I see you. Dr. Eddie, I see you. Madam Magdalene, I see you. Okay, I'll take the first photograph now. So, SPE.
Cleaner energy.
All right, the first one taken. All right, taking the second one now. Cleaner energy.
SPE.
SPE.
Yes, thank you very much.
Thanks. I can see blowout preventers. Somebody's.
Thank you very much. Have a wonderful day.
Thanks so much. This was really, really great and amazing. You have a lovely evening.
And time well spent, actually.
Time well spent indeed.
Thank you.
Thanks, Toba. Thank you.
Dr. Sarah.
Thank you, Mr. Fami. Okay. Go ahead.